Imagine you're operating an underwater vehicle in a sensitive mission. For example, it could be tracking whale migration. In that situation, you need to be invisible. No sound, no magnetic trace, nothing. But the problem here is that every underwater vehicle in some form or another uses propellers, and propellers give off a lot of noise. Propellers give off over 90 decibels of sound intensity. That is enough to disrupt the marine ecosystem and as a result compromise the entire covertness of the mission. So we asked ourselves the question, what if propulsion didn't need propellers at all? The answer to that question lies in a phenomenon called the magnetohydrodynamics, or MHD. When you pass an electric current through the conductive seawater inside a magnetic field, the interaction produces the Lorentz force. That is basically a directional push on the water itself. No propeller, no rotating parts, no mechanical noise, just pure physics. Now, MHD is not new, but early systems were inefficient and leaked magnetic signature everywhere, which could be easily detected through MAD systems. MAD here stands for Magnetic Anomaly Detection Sensors. Our project fixes that with three main innovations. Number one, a Hall-back magnet array that focuses magnetic flux inward. That is giving us 230% the thrust density of conventional designs. Number two, a PID controller on an Arduino MCU that regulates the current precisely. That is achieving under 2% speed error and 56% energy savings versus the standard propeller. And number three, we have the active degaussing mechanisms. Sensors detect the residual magnetic leakage in real time, and the MCU generates a counter field to cancel it out, making the vehicle both acoustically silent and magnetically invisible. What is the result of that? A hybrid system that switches between conventional propeller for speed and stealth MHD mode when detection is a threat.
Autonomous underwater vehicles, or AUVs, are critical for marine research, environmental monitoring, and security. However, their effectiveness is fundamentally limited by one key challenge: the inability to simultaneously achieve stealth, energy efficiency, and long-term reliability. Our literature review has identified three of these core issues. First, conventional propeller systems generate extreme acoustic noise, often exceeding 100 decibels due to cavitation and mechanical vibrations. This not only makes the AUVs easily detectable but also disrupts over 130 marine species. Secondly, these systems rely on complex mechanical components like gearbox and seals, which are highly vulnerable to corrosion, biofueling, and wear and tear that leads to frequent failures. Third, while magnetohydrodynamic or MHD propulsion systems offer silent operation, existing implementations suffer from low thrust efficiency, high power consumption, and strong magnetic signatures, making them impractical for real-world deployment. To overcome these limitations, we have developed a stealth-optimized hybrid propulsion system. Our system intelligently integrates two propulsion modes: a high-efficiency propeller for transit and a solid-state MHD thruster for silent operation. At the core of our innovation is a quadruple Hall-back magnetic array which concentrates the magnetic field internally, increasing thrust density over by 2 times while minimizing external magnetic leakage through our active degaussing system.
Let's go to the result section. So we have actually ran 30 iterations using our Hall effect sensors, real-time current monitoring, and other acoustic measurements, and conducted these tests in labs across our different universities and worked with professors, and also it was done in closely monitored containers. And the results we found, for a quick review, we at 43.1% PWM users, we got 0.5 meter per second speed and velocity, and we have been able to do it at 323 watts, whereas a conventional propeller needs 750 watts. Also, due to the use of different magnetic degaussing systems, end plates, and ferromagnetic yokes, and also Hall-back array, which is our novel part, we have been able to achieve 90% magnetic reduction in signature. And also our project, it also has a lot of potential. Maybe in future, through the new iterations of anti-fouling advanced electrodes, we can make it work, and we can also scale up this technology and work across various other platforms. Right now it's confined in a AUV, but in our country there are lots of rivers. We can use this propellerless AUVs for doing any underwater research on marine biology and also other things, and also it can be used for naval purposes as it is very much stealth, or for any covert missions. So that was basically our project. Hope you liked it.